The stair-step effect is a valuable concept in printed circuit board development, offering insights that surpass mere analysis of capacitance or inductance. It serves as a visual representation of the steps that can be taken to enhance signal performance. By observing the stair-step effect, engineers can identify and address factors affecting signal integrity more effectively. This concept illustrates the incremental improvements that can be made in signal transmission, providing a clearer understanding of how to optimize signal paths and minimize signal degradation. During a conference I attended some years ago, a presenter showcased the impact of adding coaxial cables on a weak drive signal. The audience comprised highly educated and esteemed individuals in high-speed design. When posed with the question of what they expected to happen to the signal with the addition of more cable and why, the consensus leaned towards the notion that the signal would be rounded off due to the increased capacitance or inductance. However, my rude interruption pointed out something very interesting. Upon zooming in, it became evident that rather than rounding off, the signal exhibited the stair-step effect. The additional cable lengthened the treads, consequently increasing the transition time, much akin to the effects of an inductor or capacitor. Unlike traditional analysis focusing solely on capacitance or inductance, the staircase evaluation offered insights into the physical cause behind the signal transformation, with the duration of each tread serving as an indication of the cable length. This example underscored the importance of considering physical phenomena in signal analysis, highlighting the efficacy of the staircase effect as a diagnostic tool in high-speed design. The stair-step effect is frequently mistaken for the influence of an inductor or capacitor on a signal. This confusion arises particularly when observed through oscilloscopes with limited bandwidth, where the stair-step tends to be rounded off, resembling the characteristics of inductance or capacitance in a circuit. Even on oscilloscopes with higher bandwidth capabilities, the discrete steps of the stair-step may be misinterpreted as sampling artifacts. The stair-step comprises two main components, the tread and the riser. Manipulating the physical structure of the printed circuit board directly impacts the stair-step, underscoring the importance of understanding and optimizing these physical properties in signal analysis and design. The trace length is perhaps the most direct physical attribute influencing the stair-step effect. A longer trace corresponds to a longer tread in the stair-step waveform. Therefore, adhering to the guideline of minimizing trace length directly impacts the length of the tread in the stair-step waveform. The riser of the stair-step waveform serves as an indicator of the energy propagated during the transition time of a signal. A larger riser implies a greater amount of energy being transferred, resulting in fewer round trips or steps within the signal waveform. In optimal scenarios, if the precise amount of energy required to achieve the desired voltage across the resistor is delivered, only a single trip is necessary. This scenario is represented by the green slope control signal, where the energy delivery is finely tuned to minimize unnecessary round trips and optimize signal transmission efficiency. Understanding and controlling the characteristics of the riser in the stair-step waveform are essential for achieving efficient and reliable signal propagation in electronic circuits. By taking a closer look at the riser, we can discern the factors that influence the stair-step waveform. The slope of the riser in a signal waveform reflects the rate at which energy travels from the source drive to the termination resistor. A steeper slope indicates a faster rate of energy transfer during the transition period. Essentially, the slope of the riser indicates how efficiently energy is delivered along the signal path. A steeper slope suggests that a greater amount of energy is effectively transmitted during the transition, resulting in more efficient signal propagation. When analyzing the propagation path in electronic circuits, disruptions in the relationship with the reference, such as those occurring at device-to-printed circuit board transitions, can appear as small sets of stair-steps within the overall stair-step risers. These interruptions, often depicted as mini treads in the waveform, become more extended with increased disruption along the propagation path. Longer disruptions result in longer mini treads, intensifying the rounding off effect on the signal. By closely examining the riser, we can discern the factors that influence the stair-step waveform. In this scenario, 3 distinct propagation paths are depicted. The red line signifies a uniform propagation path, the green line denotes a short duration disruption, and the blue line illustrates a longer duration disruption. The severity of each disruption directly impacts the number of steps observed over the riser period in the waveform. Thus, disruptions of greater severity typically manifest a higher number of steps, signifying more pronounced deviations from the ideal propagation behavior. The plot illustrates that merely following the guideline of minimizing trace length without addressing brief disruptions in propagation does not necessarily result in improved signal performance. In this comparison, the green line represents a 5 mm trace with uniform propagation, while the red line depicts a 5 mm trace with a short disruption. Surprisingly, the blue line, representing the electrical simulation of a 500 picohenry inductor, exhibits similar characteristics to the trace with a short disruption. This observation suggests that blindly adhering to guidelines without considering the specific characteristics of the propagation path may not yield the desired outcomes in terms of signal integrity and performance optimization. Envisioning field patterns and comprehending propagation limitations is crucial for designing resilient super high-speed circuit boards. Unlike circuit analysis, which might overlook physical board-related challenges, focusing on field behavior provides a more effective problem-solving approach in PCB development. Although validation tools are helpful, they may not always accurately identify physical issues. As developers gain more insight into applied field behavior, decision-making in development becomes more intuitive, guided by simplified mathematics. Thinking in terms of the relationship with the reference uncovers issues not addressed by traditional return path analysis, especially as transition times decrease to less than 1 nanosecond. Avoiding lateral dominant references can significantly enhance field control and noise reduction. However, mastering applied field theory requires deeper familiarity and continuous learning beyond the scope of this presentation, allowing developers to refine their skills in optimizing PCB designs for super high-speed applications.